Our next speaker will be Stephanie Chan from Michigan, who will speak on the average number of integral points on elliptic curves.
Thank you for the organizers for inviting me, and happy birthday to Andrew. And to begin my talk, I will give a conjecture by Andrew. So if you fix a polynomial with integer coefficients with degree 3 and no repeated roots, you can study the integral points on the twist family defined by dy squared equals the polynomial f of x. If you have a root of f of x, then no matter what d you take, and if this root is an integral root, then you always get sort of the two torsion points, which will be integral points as well. So naturally, if I want to count the non-trivial integral points, I will want to remove any two torsion points, which are, in this case, corresponds to those points with y coordinate equaling 2. Well, the non-trivial points are those points where y coordinate is not equal to 0, and the trivial points will be those where y is 0. Andrew's conjecture is that if we take the set of all integers up to n and count those square free integers, which gives you a twist with non-trivial integral points, then the number of such d should be asymptotic to some constant that depends on the polynomial f times n to 1/3. So actually, Andrew's original, Andrew's conjecture is for f of any degree that's greater or equal to 3. But I'm just stating this case when the degree is 3, which corresponds to elliptic curve. So if the degree is greater or equal to 5, then it's a hyperelliptic curve. Right. And Andrew also proved that if you assume ABC, if the degree is strictly greater than 3, then you get some power saving for this count as well, assuming the ABC conjecture. So ABC conjecture implies some power saving in the case that f of x has degree strictly greater than 3. But the case when f of x has degree exactly 3, he hasn't proved that ABC conjecture implies a zero density with zero density of twists has a non-trivial integral point. Right. So this result, this result implies this conjecture implies that 0% of twists when we restrict to square free integers should have a non-trivial integral point. And in this direction, more recently, it's a result by Maschke and Mujigonda that if you assume ABC conjecture and f of x is reducible over Q, then you do get a power saving in this count. So in this case, ABC conjecture also will imply that 0% of twists have a non-trivial integral. Right. So my work is kind of in this direction, but I don't want to assume any conjecture. So I'm going to restrict to some special cases. But first, I should kind of set up the way I look at these points. Or like more. Okay, if I take an elliptic curve over Q and I take the integral short Weierstrass equation, so I take the equation y squared equals x cubed plus ax plus b. A and b are integers, and for it to be an elliptic curve, the discriminant has to be 0. The sets of all integral points are the points where, x and the y coordinates are both integers. And the set is always a finite set by result of Mordell. So, before we look at maybe what happens on average or density results, we let's kind of review some things we know about pointwise bounds on the number of elliptic curves in over Q. So in the following in subsequent, well, in everything I state subsequently in this talk, I will assume that the model, the short Weierstrass equation, the model I take for the elliptic curve I study, I will assume it's in the minimal form. So in other words, if I have p to the power of 4 dividing a, I do not want the 6th power to divide b. So that's because if I do not assume this minimal condition, then you can build a curve with arbitrarily many integral points just by rescaling the rational points to get a new model with that's not minimal. So kind of want to avoid this bad case just for ease and for simplicity. And as a conjecture by Lang that assuming this minimality and assuming that you're taking the minimal model, then the number of integral points should only be bounded in terms of the rank. So this, the full generality of the conjecture is open, but in certain cases, it's proven, and this is sort of one special case where, so if you take a family of elliptic curve with bounded spiral ratio, then from this result by Hindra and Silverman, then well, this up here, this is the spiral ratio, then that will be bounded in your family, and so you will have an upper bound of c to the rank of elliptic curve for the number of integral points on this elliptic curve. So we have some kind of pointwise bound, assuming that we're taking some nice family with bounded spiral ratio, and for quadratic twist families, the spiral ratio within the family is always bounded, so you do get an upper bound of c to the rank for any within any quadratic twist family. So those are some known pointwise bounds. There are a lot of other pointwise bounds that depend on maybe the discriminant of the curve or some other quantities of the curve that sometimes may give better results, because this C here can be made explicit, but it's very large generally. So this is generally not a very good bound. And another thing to notice is that if you believe that the rank should be bounded, then the number of integral points is also bounded then. And the spiral ratio is conjectured to be bounded as well. Right, so those are pointwise bounds. If we try to do this on average, then we don't expect that many elliptic curves have even one integral points in general. Right, and if we look at some average results that are already known, if we take elliptic curves with short Weierstrass equation, and we vary A and B, and order these curves by its naive height, and consider the number of integral points on average over all these short Weierstrass equations, then it's a result by Levent that the average is bounded above by some constant less than 66. This 66 can be improved to something like 8/9 if you assume minimized conjecture. That is, if you assume that 50% of the curves have rank 0, 50% of the curves have rank 1, then you can kind of improve this upper bound here. So we get that the average bound is average number of integral points is bounded. Well, but it should really be 0 usually, and we kind of guess that it should be 0. But I guess the general case remains open. But if I restrict to a specific quadratic twist family, then I'm able to prove that in this quadratic twist family, once I remove all the two torsion points without the trivial integral points, then on average there are 0. The average number of integral points is 0. So I take the family I take, and the model I take is y squared equals x cubed minus d squared x. So this is the family of congruent number curves. And in this particular family, so the natural ordering for any quadratic family is by the size of d. And for this family, ordering by the size of d, ordering by discriminant, and ordering by naive height, they're all the same thing. And generally for any quadratic Swiss family, the natural ordering is kind of the it agrees with the other different orderings we could look at if we take the general family. Right, so this estimate implies that the number of integral points is 0. A non-trivial integral point is 0 in this quadratic family, and it also bounds the number of curves in this family that have a non-trivial integral point. So it also tells you that it's 0% of them have a non-trivial integral point. So before I kind of go into the ingredients of the proof, I just want to state kind of some related problem, a problem related to counting a number of integral points, and maybe like why we might want to count the number of integral points. So for example, if we want to study the number of elliptic curves up to a certain with discriminant up to n, it's a conjecture, and Bremer McGinnis gave heuristics to this count here, and the heuristic shows that it's asymptotic to some constant times n to 5/6. The constant can be made explicit. I just didn't write it here. It's given by some very explicit formula. And counting elliptic curves in this family is the same as counting number of integral points in this family of model curves. So that's because there's some natural invariants for elliptic curves, normally numbered as C4 and C6, which kind of fits into this X and Y here, and you're counting the number of elliptic curves according to these two invariants, and they give you a relationship between sort of the two invariants and the discriminant. So you're just counting the number of integral points with in this family with this discriminant up to n. And that's maybe why we're interested in studying integral points in some family. And in this direction, by using some similar methods, I applied for the congruent number curve family. I took a model curve and I twisted by d. But now it's a cubic twist, so this k will be something that's fixed. D will be, if I want to keep this equation minimal, I will need d to be cube free. Yes, I'll vary the d here. So this is a cubic Swiss family instead of a quadratic Swiss family, but some of the structures are similar, and I'm able to show that 0% in this family have have an integer point. Okay, so but in this particular statement, I'm assuming that k I'm assumed to be not 0 and not 1 and square free. 0, if I take k equals 0, it doesn't really define a proper family. If I take k equals 1, in this particular case is excluded because there are. Okay, so as written, this statement wouldn't be true because there will be, if we plug in x equals 0 and y equals d, that will give me 3 torsion points and also an integral point. So if I take k equals 1, there are actually some 3 torsion points that are also integral points in the family. So as written, it's not true, and we will need to remove the 3 torsion points here. But k equals 1 is kind of work in progress, and if I have time at the end, I will maybe state the result. So I think the next step is to go into the proof. I'll sort of say some ingredients that go into the proof. the reason I took this congruent number curve family is because there's a lot of control in it in terms of, because it has full rational to torsion, you could do two descent very explicitly. And this is something that's studied by Heath Brown. He showed that the moments of the two Septembres, well, he computed all the moments of the two Septembres in this family. Right, so S, the set S here is just a set of square free numbers up to n. He computed all the kth moments of the two September in this family. Okay, so with this moment calculation, if we apply the known case of Lang's conjecture, because I mentioned that Lang's conjecture is true for any quadratic twist family, if we combine it with so you get an upper bound of c to the rank for the number of integral points on each curve, and if we use the size of two September to bound this, right? If we need to take, so this k will not be the same as this k here, but if you take here k large enough, it will give you an upper bound that bounds a number of integral points, and because here the Heath Brown's result implies that the moments are all bounded, then applying the upper bound from Lang's conjecture, you also get that the number of integral points, the moments of them are all bounded. But the bound would depend on. So that's a convenience in showing in bounding the average number of integral points, because then you can use Cauchy-Schwarz or something to remove say some bad d's. If you have some bad d's that you want to remove, you can Cauchy-Schwarz it using this this bound on the moment. Okay. So right, okay, so now I'll actually go into the proof. So the main sort of main thing that goes into the proof is that I, instead of counting the integral points directly, I'm going to count certain integral quartic, integral binary quartic forms. They are given, or in this form, ABC are integers. There's some relationship between C and A, but that's not too important in terms of counting. And the discriminant of the these quartic forms are related to the elliptic curve, the discriminant of the elliptic curves. I've actually missed out a D here, so this is E sub D instead of E. So okay, so if I fix D, then I have a set of integral binary quartic forms with this given coefficient. And something to notice is that they all represent 1. If you just plug in, so trivially, if you just plug in 1, 0, then it gives you 1. So that they're all forms that represents 1. If you just try to count the integral forms that you get out of this, you will get n discriminants to count. Then you kind of expect that there are n points. So just by counting the quartic forms, just by counting general quartic forms, it's not enough. You cannot. Okay, so what I mean is you cannot drop this condition that f represents 1. So that's where you would get the saving. Right? If you drop the condition that f represents 1 and just generally count the number of quartic forms with this discriminant, then there should be like the order of this should be n. So you do need that f is in this form that represents that they represents 1. So that gives you where the saving is. So that's something I cannot remove. But the idea is I could transform the quartic forms that I get into something with a smaller discriminant. And I will just show you the lemma. So this is kind of the process. It's just a simple transformation. I'm just transforming all the binary quartic forms to something with a smaller discriminant. But the condition I need to satisfy is that I need this P here. I could pick any P. actually I write P, but it doesn't have to be a prime because of Chinese-Remainder theorem. But suppose P is a prime for just for convenience, then I need P to divide D, and P to not divide the x coordinate of the integral points. So this is kind of something that's hard to control. Well, P dividing D just kind of restricts the P we can choose, but P not dividing X means that we need to know something about the points. So the reason of transforming this, doing this transformation is that now I have smaller discriminants. I have a set of binary quartic forms, but now they're in a set of, they have discriminants little o of n if you pick P large enough, with a cost of sort of changing what these form represents. Okay, so there are, okay, so so the hard thing would be to control, to show that this choice of P exists in order to get enough savings. So if I want, so if I want to find P of some, if I'm able to find P with some large enough size, then I'm left with little o of n of forms. And this is something I could control using Heath-Brown's argument. So it's in Heath-Brown's work on the average, on that two-September moments, you can kind of extract information about the GCD of, okay, I should have written it here, but okay, you can extract information about the GCD of the x coordinate of the point and D. Okay, so that the reason is that this GCD of between GCD of x and D is controlled by exactly the image of the point in the two-September. So you can map all these points to the two-September, and the two-September element itself would still have the information about the GCD of x and D. So by sort of taking Heath-Brown's argument, certain parts of Heath-Brown argument, I can extract certain information about the GCD of x and D, and I can control the size of GCD, control the size of GCD between x and D, so that I can ensure I can pick a divisor, an auxiliary divisor P to apply this argument. So I need P to not to be kind of large, so that I can get a saving, because now that the discriminants are n divided by P to some power of 6. So that's that reduces the set of discriminant that I'm working with. But I also can't actually pick P to be too large, because now I need to control the number of points that represent the number of points that kind of maps into the same two-September element. So in order to bound this, I will need to apply some bounds on the two-ways inequality, which to apply known bounds, we need the discriminant, the resulting discriminant to be not too small, and as long as P is not too large, I can control the number of points that gets mapped to one single two-September element. So I use Heath-Brown's work to control the size of P I can pick, and the argument kind of works with P. I can always fix P roughly of the size of the e to the some small power of log n. So that's the idea of the proof. And since I have some time left, I'm just gonna mention sort of work in progress. That is the cubic twist case that I missed out in the statement. So before I talk about the proof, I stated the cubic, the statement for the cubic case, which is that the 0% of cubic twist of Mordell curve has an integral point, but I remove the case when the twist is the set. I'm removing the twist of the case when k is 1. So this is so replacing b by d squared is exactly the case I kind of removed. And turns out that this case, you can kind of do a very similar thing as what I did for the congruent number curves, because now because of there's an isogeny between, you could take the rational 3 isogeny, and that gives you, if you look at the September, the phi September of these curves, you will get something, you will get some cubic forms which are very explicit, which you could just kind of write into a cubic character sum, and then you can kind of do the same thing as here from, but with cubic characters, with cubic residue symbols instead of quadratic residue symbols, and you'll be able to compute the moments of the phi September in this family. But something that's very different from the congruent number curve case is that these phi Septembers diverges. So in the Heath-Brown case, the k September always converges to some finite number, but here in this cubic twist family, these phi September diverges, right? And in this cubic twist family with a -27 coefficient, this is saying that there's only on average, the only class that's in this sum is the trivial class. So there's no other non-trivial, on average, there are no non-trivial classes in this particular family. So using some certain parts of Heath-Brown's arguments, you could do the same thing and control, again, GCD of between x and d. Then that gives you some way of controlling the average number of integral points. So in these two families, I'm able to show that on average, the number of integral points, well, non-trivial integral points is 0. So here, this 0, plus or minus d are just the 3 torsion points. So these are 3 torsion points. I'm removing the 3 torsion points, and right. So after I remove any trivial points, I get what I expected, which is that on average there are 0 integral points. Okay, so I will stop here, I think. Yes, yeah, I haven't tried that. Yeah, that's a good point. So this is you would do the 3 isogeny descent, so not the 2 torsion. Yeah, there's no 2 torsion here. There's only 3 torsions. That's what I would want, but I don't know how to do it. to descent, yeah. No, it's just to descent, yeah. I haven't tried it, but I think it's not as nice. I think what you get is not as nice as in these two cases. Yeah, the equation you get, that's different. I think it's harder to count. I think you have to do some quadratic residue symbol, which is can be a pain. Can be a pain. Yeah, but I haven't really thought about it. Power of so in this cubic twist family is different from the Heath-Brown's family. So in the Heath-Brown's family, from looking at the 2 September, you get that the GCD is like kind of in the middle. But for this family, a lot of the GCD are very large, actually, I think. Yeah, maybe I'm not sure how to answer that question. It's not a corollary. You need to take certain parts of the argument. You need to count the bad ones that you don't want from the sum. So it's not a consequence. It's from so what you get from the September groups are some cubic equations, and if you look at cubic residues, if you take a prime that's 2 mod 3, then any integer is a cube mod that prime, I think, and that's kind of where the extra stuff is from. So that sum is actually the sum of the sum of 3 to the number of primes that are 2 mod 3, something like that. Yes, 2 sorry, but they just do the 2 descent directly. So you go back and yes, it's yes, kind of, yes. Yeah, 3 to, it's 3 to the number of primes dividing that number that's 2 mod 3. Yes, I think so. If you restrict to the D's where you only have 1 mod 3, the primes are 1 mod 3, then you should get something finite. So it's only because the contribution is only from the primes that are 2 mod 3.
Let's start with Stephanie again.